Okay, let's solve this problem, which is a second order problem for a reaction where some reactant A goes to products. The initial concentration of A is 5 molar, and the first two half-lives are 25 and 50 minutes, respectively. Although there is nothing in this problem suggesting that it's a second order reaction as opposed to a first order reaction, other than the title right up here, how would you determine that this is a second order reaction? Well, oftentimes you have to look at the information that you've been given and interpret it based on what you know. For example, it's telling us the first two half-lives are 25 and 50 minutes. Because the second half-life is twice the first half-life, this indicates that this is a second order reaction, even though it's not stated explicitly in the problem. We're then asked to write the differential rate law for this reaction, calculate K, and then calculate the concentration after 525 minutes. Because it's a second order reaction, then we know that the rate law, or the differential rate law, will simply be equal to rate multiplied by K, that concentration raised to the second power. To calculate K, we could look at all of the different equations that we know for a second order reaction and recognize that one of them allows us to use half-life in order to get K, or knowing K, we could get half-life so long as we have a concentration. It turns out that we do have a concentration, an initial concentration. We do have two half-lives, so we should be able to solve for K by plugging in our concentration and our half-life. But what half-life should we use, the first one or the second one? Well, we always use the half-life that corresponds to the concentration we have. This is the initial concentration. The initial concentration is used to determine the first half-life. If, however, we were given the concentration after the first half-life, which would be 2.5 molar, then we would use the second half-life. So 25 minutes is what we will use. We'll rearrange the equation and solve for K, and we get a K value of 0.008, 1 over molar minutes. Again, remembering what our units should be based upon the order of the reaction. If I did want to use that second half-life, then as I mentioned, I would need to use the concentration after the first half-life, and in doing so, I would obtain the exact same value as I obtained before. For part C, to calculate the concentration after 525 minutes, now I have a question that's relating concentration and time, and concentration and time are related through the integrated rate law equation. So 1 over the concentration at time t is going to be equal to K times t plus 1 over the initial concentration. So I will plug in the K value that I determined, plug in my time for which I'm attempting to solve for the concentration, and then plug in 1 over the initial concentration. This gives me a numerical value that is equal to 1 over the concentration. Don't forget that when you use this equation, you are solving directly for 1 over the concentration. So I would need to take the reciprocal of that to get my concentration at time t being 0.23 molar.